Hello, this is the last video number 5, and I will introduce the scalar and vector potential phi and A of the field. In some other videos, I will present the four-vector formalism of electromagnetic theory using the four-vector potential A and phi. Now the scalar and vector potential phi and A came into scene when we realized that the magnetic field B equals cross product of del and A satisfy the third Maxwell equation, which is del dot product of B equals to 0, because this expression is always equals to 0 according to tensor and vector analysis. Now, if we put this expression of B in the second equation of Maxwell's, we have this from this equation, we have this expression, and we can switch the del and the time derivative, and finally capital E is equal to minus dA over dt. Or you can put it in the left hand side, and we have the equation capital E plus the derivative of the time derivative of A equals to 0. Now, if we apply the cross product to this expression with the del, we get this. And remember that when the curl of a vector is 0, like this, it must be the A, the gradient of some scalar field. A equals minus del phi. Therefore, this expression from here must be equal to minus del phi. And the electric field and magnetic field is with the scalar and vector potential, they have this expression. But the vector potential A is not uniquely defined, because if we put A prime equals to A plus del lambda, where lambda is a scalar, then B equals cross product of del and A prime equals this one, and finally, because this is always 0, finally the dot product of A prime is equal always to the cross product of A. Therefore, A prime is always equal to A plus del dot of lambda. A prime and A have the same curl and give the same B. They do not need, although, to have the same divergence. Therefore, if to this expression we apply the divergence, the dot product of del, then we have this one. And the electrical field, capital E, is equal to minus del phi minus dA over dt equals the same with the prime expressions. And from these two equations we have del dot of phi prime minus phi equals to d over dt of A minus A prime, and from here we have the expression phi prime equals phi minus del d lambda over dt. In fact, and by suitable choice of lambda, we can make the divergence of A prime anything we wish. The choice should be made to get the greatest mathematical convenience and will depend on the problem we are doing. This procedure is called choose a gauge. For electrostatic and magnetostatic, we choose the Coulomb gauge, which is the divergence of A is equal to 0. And for electrodynamics, the is equal to minus 1 over c squared times d phi over dt. And it is called Lorentz gauge. Now, we have electrostatic and magnetostatic. Electrostatic is defined when the magnetic field B is equal to 0 and the Maxwell equations are divergence of E equals rho over epsilon naught and the cross product of del with E is equal, or the rot of E is equal to 0. But when the rot of E, of the curl of E is equal to 0, that means there is a potential phi such that E capital E is equal to minus del phi. And therefore, from previous equations, the square of del dot phi is equals to minus rho over epsilon naught. Magnetostatics means that d E over dt is equal to 0, and the Maxwell's equations are the divergence of B is equal to 0 and the C square times the curl of B is equal to J over epsilon naught. But remember that this expression becomes from from vector analysis is this one, and because we choose the Coulomb gauge, this one, as we have said in magnetostatic, we choose the Coulomb gauge, which means that this is equal to 0, then we have this expression for the magnetostatic. This is for the electrostatic, and the corresponding equation for the magnetostatic is this one. Now about the vector B and the vector E, the magnetic field B and the vector potential A. For a long time it was believed that A was not a real field. It turns out, however, that there are phenomena involving quantum mechanics which shows that field A is in fact a real field. One of the most striking manifestations of this is the Aharonov-Bohm effect, where quantum particles are influenced by the presence of a vector potential A even in regions where the magnetic field B is strictly 0. These experiments demonstrate that the potentials, not just the fields derived from them, have fundamental significance in quantum mechanics. Thank you very much.